Okay, good afternoon, everyone. Today, second seminar speaker we have Wenting Hu. She's doing her PhD under the supervision of Professor Tutumler, and naturally his research expertise is related to geomaterials in transportation infrastructure. She specializes in characterization of aggregate byproducts, modeling organic materials using discrete element method, and the numerical analysis of the dynamic response of track structures. Please welcome Wendy.
Thanks, everyone. Can you hear me? Like, is this mic working? Okay, cool. So I'm Wenting, and today I'll give the presentation for evaluation of ballast behavior under different tie support conditions using discrete element modeling. So basically, my PhD topic is to develop a numerical model to simulate the train and the track interactions. And today, this one is without trains, so it's basically focused on the ballast behavior. So let me give the outline of today's lecture. So the first one, I will talk about the background of our research, and then the objective is approach, and then it's the ballast support condition model, and also its calibration with the laboratory testing results. And then the findings related to static loading and the findings related to dynamic loading. So first of all, in the US, we have most of the railways that are constructed with ballast bed, which means that it will look like this. They will have rails on top of these, and this is the cross tie, and under the cross tie there is the ballast layers. So these ballast layers, when we have repeated loadings on top of it, it will develop non-uniform support conditions. For example, this is one of the support conditions we study in our research. This is the lack of center support condition, which means that by loading, repeated loading, some of the particles are going to the side instead of the middle, so it will create this kind of support conditions. So this is an introduction like why we would care about the ballast material, because they can have non-uniform support conditions rather than the uniform ones that are usually supposed in all the other researches. So this is the a current study that by Realtek in our department, that they have some field instrumentations along the northeast corridor, which they have different zones, and they implement their strain gauges. So with their implementations, they are able to determine the support conditions in the field, where they find that they have multiple types of support conditions. It's not like uniform, like you can see all the like the forces are the same, but it's varies a lot, which means that in the field, actually, these kind of non-uniform support conditions exist. So this is the initiative of our research, which is the Amtrak cross-tie design research. So the Realtek group, they are more focused on the cross-tie part in this research, and we are more focused in the structures of the ballast materials. So why are the support conditions matter? So there are some previous literatures that are studying the support condition influence. So for example, this study that in 2009, they do a study for cross ties. So they have different support conditions. For example, they have non-symmetric ones, like symmetric ones, and these kind of symmetric, but one side is larger than the other. So with different type of support conditions, they find that the critical bending moment in cross ties can differ a lot, as far as 8 times than the uniform ones. And also there's another study focused more on the ballast part, that is the influence of ballast conditions to the tie ballast interface. So that means they have, when it is new materials of the ballast, they can have pointy loads on the cross ties. And with degradations or some types of changings of the materials of the ballast layer, then they can have more uniform types of support conditions. So all of these studies show that the support conditions really matters to both cross ties and ballast materials. And in our study, we are more focused on the ballast materials. So how and these support conditions will influence our ballast particle behavior and its performance. So our objective of this research is to evaluate the influence of support conditions on ballast materials. So we have two types of loadings. First is the static loading, which means we apply a static load on top of the cross tie for different support conditions. And for static loading, we compare the tie ballast interaction, which means it is the surface of the bottom of the cross tie and how it interacts with the ballast particles. And the second one we look into is the ballast particle performance, which means what is the contact force chain in the ballast layer and what are the stresses in each ballast particle. And the third one is the ballast subgrade interaction, which means at the bottom of the ballast layer, there is a layer, it's the natural soil layer, we call it subgrade. So the interaction between ballast and subgrade. So after the static loading, we also study the dynamic loadings, which we apply 4 different types of loadings, representing both freight trains and also passenger trains at different level of speed. So for the 4 different types of loadings, we see the velocity effects of these loadings on the ballast behavior. And also we investigate the contact force chain change during the cycles of the dynamic loading, and also the permanent deformations. Today's topic will more focus on the static loading part, and we will show a later results of the dynamic loading because these results are not published yet. So the research approach. So how to simulate this kind of support conditions? So we utilized a model, a type of model, which is called discrete element model. So discrete element model is really used to simulate those granular materials. For example, these are ballast particles. These are granular materials, which is one by one. They're not continuum, like usually studied by FEM. So in these granular materials, we can use the discrete element modeling method to model this material and study their interactions. And here we utilize the method of block 3D, which is developed here in the University of Illinois. And this DM can be calibrated with the previous laboratory results, which is here. So the Realtek group, they have done a bunch of laboratory testings in their facilities to study different high support conditions. So we'll talk later about what different support conditions they choose. So we can compare our DM results with their laboratory testings to calibrate our model and then simulate the field performance. So these are the 5 support conditions that the Realtek group they did in their lab testings. The first one is the lack of real seat support. So in their lab testing, by changing, this is the rubber pad, the blue ones. So by changing the locations of the rubber pads underneath the cross tie, they were able to simulate different types of support conditions. So for this one, this is lack of real seat. So these are real seats. So lack of real seat support condition. And these are the full support condition, which is the ideal support condition, usually is encountered in the designs and simulations. And this is the lack of center support conditions, which means it's more like this. So they will have a gap in the center. And this is the high center support condition, which is the center is a little higher than the side. And this is a severe center support condition. This is a more severe condition than this high center support condition. So we are able to simulate the exact same support conditions in our DM models, like shown here. So here are the some of the parameters in our discrete element modeling. For example, the cross tie is a concrete cross tie, so the dimensions are shown here. It is 10 by 9 by 102 inches. And the ballast layers, it is assumed to be 14-inch thick. So this is the Euro thickness for a ballast layer in the field. And it is 24-inch width, which means, and also it has a slope of 2 by 1. So totally, for one model like this, we have one tie spacing. So this is the 24-inch is a one tie spacing, which means this is this tie spacing. If you have another tie, the center of the tie will be here. So by creating this kind of model, we totally have 11,000 particles in this one model. And totally we have 5 models, so we have 55,000 ballast particles in our models. And in our discrete element model, these are the parameters we choose. So the ballast, we need to give their gradations in the modeling. So we choose the gradation that are in the specs of the ARIMA 3A, and also the shape properties. We obtain these shape properties from the field that we collect a bucket of the ballast in the field and scan them using our machines of the scanners that Professor Tutumlar's group have. And by scanning these particles, we are able to get their shape properties as flat and elongated ratio and also angularity. And in the DM model, we also create the same properties in our DM model. And some of the other important parameters are listed here. So these are the parameters we utilize in the DM model. And after choosing the models, here is the model calibration with the laboratory testing results. So totally we have 5 different support conditions. In the lab, they apply 10 kips of load to each real seat locations. And we apply the same loading in our DM model. And so for different types of support conditions, you can see that using the same parameters, we don't change ballast gradations, we don't change any parameters in the ballast layer. We're able to get a similar result with the laboratory testings for most of the support conditions. For example, like this is the lack of real seat support condition. We can see the dashed lines are the lab testing results, and the solid lines are the DM results. And they match pretty well in the trend, and also the percentage force taken by each of the segment. So the segment here means that correspond to the segment here. So we divide the bottom of the cross tie into 6 as the same as the laboratory testing, and we calculate the contact forces at each segment in our DM modeling to compare with the lab testings. So one exception is this one. This is the full support condition. You may see that for the other ones, they match pretty well in the trend and the magnitude. But for this one, they don't match with the trend. So the reason is in our DM modeling, we create a cross tie like here. But we are not able to bend this cross tie because in our discrete element model, this is a drawback that you can never bend a block. So this one, we cannot bend this, this cross tie in our DM. But in reality, you can imagine that if you apply loading on here, they will bend like what's shown here. This is the lab testing results. So the place you apply load will have larger force, but we are not able to simulate that bending effect. And also, there can be some problems with the first contact, because some of the part of the ballast make contact with the cross ties first, then the others. And this can create a little non-uniform support conditions in the full support condition scenario. We can explain later with our visualization results why this happens. So after the calibration, we see this set of parameters are working for most of the cases, and we see that this is the calibration process. And then we continue to do our simulation. So for the static loading, we are going to study these 3 aspects. So the first, we need to calculate the stresses. So the force without rotation and force with particle rotations are listed here. These are from the literatures. So we utilize these equations to calculate the stress tensors in each of the ballast particles we have. And we are more focused on the vertical normal stress, which is in the vertical direction instead of lateral or longitudinal direction. So for the vertical normal stress distributions, these are the visualization results. So this is for the same as the laboratory testing load levels. The real seat load is 10 kips. So you can see that for this one, this is lack of real seat support condition. And you can see that the colors indicate the magnitude of the stresses in ballast particles. So it is more red or black, then it has larger magnitude of the stress. So you can see that for lack of real seat support condition, most of the stress are concentrated in the middle part, and especially the top of the middle part, particles that contacting with the cross ties, they have the largest stresses. It's almost in a black color. And for this one, this is the force support condition. When we compare full support with lack of real seat support, you can see that most of the colors are either white or gray or in the yellow side of the color, which means that they have less stress levels than the lack of real seat support conditions. Similarly, for the other support conditions, this one, the lack of center support, the forces are more concentrated on the two sides, especially for this one. You can see that the left side takes more stresses. This is because these are granular materials and they cannot be simulated as perfect condition. So for this case, the left side contact with the cross ties first, so it has larger stress levels. And for this is the high center support condition. As you can imagine, the center part has more stresses in the particles, and this is severe center condition, which means it's most of the particle contact with the cross tie are within very limited area. So the stresses are very concentrated on this scenario. So as you can see that before we visualize these results, we can't imagine which particles take stresses among all these particles, 11,000. But with this visualization, we are able to see that which particles take these stresses and forces. So the shoulders doesn't take a lot of stresses. So most of the stresses are located in the area with good contact with the cross ties. And they don't diffuse a lot as we imagined before that to the side, but it's more concentrated on the vertical direction of transformation of these forces. So one problem with this type of high stress is that in the real field, if you have such high stress, it may break the particle, so your ballast layer will degrade. So this is the visualization results still for the vertical normal stress distribution, but this is for 20 kip. So as you can see, that they follow the same pattern with the 10 kips of loadings, but like the stresses of each particles are higher than the 10 kips. And this is the visualization results of the contact force, because we want to see if we apply a force on top of the layer, how does it transform to the bottom of the layer. So these are the results of our analysis. So the contact force network in the ballast layer are shown here. And the color and the thickness of the line indicates the magnitude of these forces. So as you can see that the forces are mainly concentrated on a few critical paths. For example, for this lack of real seat support condition, you can find a few critical paths. This is one critical path. And for the force support conditions, these are the critical paths that occurred in this ballast layer. So coming to the previous results, that we can see the non-uniform support in our DM results for the force support condition. You can see here, our force support condition, it is assumed to be uniform in the ballast layers, the force chain, but actually the left side takes more stress and forces than the right side. This is because that, as I mentioned earlier, a few of the particles on the left side, they contact with the cross tie first, and then they take that force chain instead of the right ones. So similarly, for the lack of center support conditions, the critical paths are here, and you can see a few like the diffusion of the force to the center and also to the side, but most of they are like verticals, directly from the top to bottom. So similarly for the other two conditions, for high center and severe center, the force chains doesn't have a large diffusion angles to the side, and only a few paths will take most of the force in these scenarios. And similar things for our real estate load of 20 kips. This is the same strength as the 10 kips, but the only difference is the magnitude is a little larger, and you can find a little more thick lines and darker lines compared with the 10 kips of real estate load. So why do we care about the forces among the particles? So the tie ballast contact pressures, because they will, if you exceed a certain amount of the pressure, they will detriment not only the ballast particle, but also the cross ties. For example, in ARIMA, they have allowable pressure on this tie ballast interaction that is not detrimental to their cross ties. So their allowable pressure is 85 psi. So look at these, which of the like support conditions and loading levels will exceed this allowable condition. That for different types of support conditions, the black ones is the full support. It performs the best. So we have different types of seat loadings from 10 kips, 20 kips to 25 kips. So all the threes of loadings for full support condition, they satisfy the allowable ARIMA, like allowable maximum pressure at the tie and ballast interface as 85 psi. But for the other four type of support conditions, for example, the most critical one is the severe center binding support condition. So when we apply 25 kips, it can have as much as 154 psi in the pressure of the tie and ballast interface, which is exceeding 30% of the allowable pressure. This will be a problem in the field if this kind of support condition creates. So by studying different support conditions, we can see that we have to select one or a few critical support conditions that the railroads have to pay more attention to and schedule their maintenance accordingly. So when we look at the ballast particle contact force between each other, we can see that, so this is the contact force, and this is the percentage of the particles passing that force. For example, all of the particles are below this 6,000 newtons of the contact force between each other. And this is the crushing limit we found in the literature. When they do laboratory testings, they found that their crushing limit is around 6,000 newtons, which means if you reach this amount of contact force, the particles of ballast will break into two parts directly. So in our case, all of the support conditions, they don't exceed this contact force of crushing. But as we see, this is the total crushings, but usually it's not going to split into two parts directly. Some of the particles will still, for example, if they exceed 4,000 newtons, they may still have some breakage at the edges and create smaller particles. And those smaller particles will have some influence of the drainage in the ballast layer, and the drainage will create more problems. So basically, the contact forces of the ballast particles will create a problem of possible degradations in ballast layer. And again, like for the best one is the full support condition. It has the lowest contact forces, which means the most of the particles are below 2,000 newtons of contact force. And the most severe one is the lack of center rail support condition in the ballast particle contact force perspective. And we will look at the ballast subgrade contact pressure, which means the contact pressure between the ballast particle and the subgrade. As we can see in our case, we have ballast and subballast equals to 14-inch, and we apply the static loading as 20 kips scenario. This is to be mentioned that while we choose this is the field loadings of the railroad. And when we compare with the RIMA design procedure, we can see that in our design model, in our DM models, the four of the support conditions, they have the ballast and subgrade pressures lower than the RIMA calculated. This is an empirical design method. So these four are below that method. but a severe center bindings is much higher than this method of empirical, which means if you design using the ARIMA method to design your ballast thickness, but if you have the severe center binding condition, then you will have some problems of your subgrade because your pressure will be higher than your bearable pressures in the subgrade layer. So as a conclusion of the findings related to static loading, only a portion of the ballast particles will participate in the load distribution if you apply an external load. And particles on the shoulders and particles in the area with poor support conditions often experience none or very low stresses under external loadings. And in our case, the severe center binding scenario seems to be the most critical condition in terms of a high tie and ballast contact forces. It will exceed the ARIMA allowable pressure by over 30%. And the top of subgrade pressure also calculated from the DM model, and the maximum of all the support conditions except the severe center binding, they are below the calculated pressure from the empirical design manual. But the severe center binding scenario will have much larger, so it will have problems in the designs. So when we see the dynamic loadings, I will show you some of the visualization results, not the quantitative results, because the quantitative results are still trying to get published in another journal. So in the dynamic loading part, we choose two types of loadings. One is, if you cannot see it clearly, this is the freight train locomotive, and this is the passenger train locomotive. So they have different geometry configurations. For example, like the axle spacing are different, and the loading levels are different. As you can see, this is almost twice of the loading levels of the passenger train. Because this freight train, we choose actually the BNSF freight train, which is the 286 kips of tons of the total weight. And this one is, the passenger train is from Amtrak, so it is 143 kips. So it's basically 2 times of the loadings. And also they have different speed. As we all know that freight trains have lower speed, so we choose 2 types of speed. This is the 20 miles per hour speed, and this is a 50 miles per hour speed. And for passenger trains, we choose 110 miles per hour speed. This is usually happens in some of the like if you have a transition zone, for example, if you are crossing a grade crossing, or if you are encountering a bridge, then they are traveling at this type of speed. And in the northeast corridor, they can travel up to 150 miles per hour. So by choosing the dynamic loadings and apply a loading of 1 train passing, which means 8 cars and 32 wheels, we are able to do the simulations in our DM model. So before I see the results, I would like to show you what we do in our DM model. It's because if we want to apply a force, for example, the blue ones is what we apply into our DM model, and the green ones are the contact force we obtain from our DM model. So basically, we want it to be the same. For example, if we give it 1 force, 1 Newton of the force, we want it to give back 1 force of Newton. So it makes sure that this force is applied successfully in our DM model. But without doing anything in our DM model, we are not able to give this dynamic loadings into it, because the obtained ones are different than the applied forces. So what we do is we apply a PID function controller to our DM model. And with this controller, it is more like your cruise control in your car, that it will automatically adjust your force input into this DM model. So by giving this controller, we are able to get exact same force as we applied into our DM model. So by successfully applying the load, these are the results we get. So I only show one example for full support condition. So this is the force chain in a cycle, that how it changes in a full support condition. So as you can see, if we don't apply a force, so one thing is this is not a full, this is because we don't apply force, but still this cross tie will have its own loadings. And also this is from one of the cycles we give. So previously it has loadings. That's why this is not 0. So this is the, like when we first apply loadings, you can see some part of the particles will contact with the with this cross ties first. And then we increase the loadings and the force change will become to change. Like still this is the critical path from the first loading conditions, but the other part starts to take forces. And then this is the peak of one cycle of the loadings. So this is almost a full support conditions, you can see. And similarly, this is the when we decrease the loading, and this is when the loading is decreased to 0. So with this dynamic loadings, we are able to visualize the force change in a cycle and in different multiple cycles. And I will show you, this is like the simulations of the support conditions and how it changes within a cycle of loadings for four support conditions. And similarly, this is the lack of center support condition, the contact force change, how does it change within a loading. So one thing you can notice that is it is not always the same that which part will take more loadings. For example, sometimes the left part will take more loading, but sometimes the right part will take more loading. So dynamic explains how these granular materials will interact with the external loadings. And this is the high center support condition. So most of the, if you cannot see it clearly here in the presentation, so these parts are the shoulders, and it doesn't have a lot of force changes. And this is the lack of real seat loadings. So sometimes the middle part will take more forces, and sometimes like this side away from the real seat will take more loadings, depending on the loading cycles. And this is the balanced particle velocities with vector plots. So basically we studied the 4 different types of support conditions, because we omit this severe center bindings because it is not very common in the field. And these 4 support conditions, you can see that the vector plot of velocities and different colors indicates different directions. For example, the red colors indicates it's moving toward the left, and the black colors indicates it's moving toward the right. So as you can see that the most severe support condition is this lack of real seat support condition. So the vectors are in a much more larger magnitude in the velocities of the particles, which means that if the particle velocities are larger, that means the deformations will be larger in this scenario. And the 4 support conditions have the best velocity vector plot because only the particles of the side will change. That is because it doesn't have any constraint on the other side. And most of the particles in the middle part will remain the same locations or only move a few, but not a large distance. And these are the vibration velocities of our ties. So for 110 miles per hour passenger trains, the velocities are plotted here. So for different types of support conditions, as you can see, the lack of real seat support conditions, it has larger velocities compared to the other velocities. But these velocities are not in a significant difference in the magnitude if you compare different type of support conditions, which means support conditions is not critical to tie vibration velocities. But as I didn't show here, but we actually find that different speed will have a major impact on these support conditions. When we compare different speed of the same train, the larger speed will have like twice of the magnitude of the velocities we have in ties. And also the freight trains, even though they have lower velocities, but they have larger tie vibration velocities than the passenger trains. And this is the permanent deformation results, is that when we give numbers of loadings of the dynamic loadings and compare the results for different support conditions for a permanent deformation perspective. As you can see, the ideal case of the full support condition, which is normally what is studied by the other researchers, it has the lowest permanent deformation. But if you have a lack of center support condition or lack of real seat support conditions, the permanent deformations, even though it's only for 1,000 repetitions of the loadings, it can have much higher deformations than the full support conditions. So the findings related to our dynamic loadings is that the ballast particle velocities, we are able to capture them from the dynamic loading conditions. And the lack of center support condition and lack of real seat support conditions, they show that the trend of moving toward one side of the track, which means that it will be a problem if it moves to one side of the track that will lose their lateral stabilities of the track. And the force chain network during a dynamic loading cycle can be visualized. And among the 4 studied support conditions, lack of center support conditions is found to be the most critical one because it has the most permanent deformations when we have 1,000 types of repeated loadings. And that's all for today's presentation. I would like to acknowledge the co-authors of Bin, Feng, Wei Li, and Hussein is one of our group mates who also help us with some of the DM modelings. And Riley and Marcus and the Realtek group, they provide us a lot of materials of the laboratory testing results. And this is a project that is funded by the Amtrak study. And finally, Dr. Yu Qian, who is previously a student here, also help us with the problems in DM. Yeah, that's it. Thank you.
Does anyone have any questions?
Yeah.
Ladies first.
I was wondering if, great presentation by the way.
Oh,
the
thanks.
visuals are really nice. But I wanted to ask if during dynamic loading, can you consider the reorientation of your element of it going through that time?
That's a good point, actually. We are able to do that, actually, but we didn't do it like in this study because we are able to find the locations of the centroid of each particle, and we are able to see where is their edges. So by if we chase where is their centroid and where is their edges, we are able to see the rotations, but we didn't model them because this is not on direct results. We cannot see the visualization results directly from our DM. We only have their metric results. For example, their locations, their edges, and their forces. So we have to manipulate with it to get the rotation. But I will guess yes, because this is the ballast material here is not breakable. So the way that they have permanent deformation, it's basically because of the rotations. Because they cannot break, then probably it's rotations and then a little compressions.
Prior to dynamic loading, you mentioned that the high center was a critical case, and then after dynamic loading, it became the lack of center.
Yeah. So it's a great question, actually. So so because for a perspective, because if you look at the ballast and the track substructure, actually it has many perspectives you have to look into. If we look at the tie ballast interaction, then as we said, the center bindings, especially the severe center bindings, is the most critical because it has the largest force in that interface. And that is basically because it's detrimental to the cross ties, because they want to limit this pressure in order to keep their ties safe. But if we look at the permanent deformation of the ballast layer with the repeated loadings, actually we find that lack of center support condition is more critical than the other one. So which means that if you look into different aspects, they have different conditions that is more critical.
Is this sort of condition due to that dynamic loading because it's moving and you're using that center?
What was the question again?
Like the permanent deformation, where is it measured
So we basically measure like the top layers, because in our model, like the bottom is fixed. We cannot the bottom cannot be changed. So we basically measure the top layers. For example, what is the height of the ballast layer? At the first beginning, it's 14 inch, and then at the after 1,000 loading cycles, we also measure the top layers. What is the and calculate the thickness by like dividing it by the subtracting it with the centroid of the bottom ones. Then we are able to get the permanent deformation. Mm-hmm. Yeah.
I have a few questions. Thank you for
Sure.
You mentioned something about the technique you were saying that you cannot bend, right?
Yes.
So how I don't understand how you
We actually cannot overcome it right now because I think they are still some of the like DM models. For example, PFC. It's another like commercial software. It will cost a lot of money to purchase the license, and in there, like they are able to make it bendable by giving that block some of the components. Maybe the block itself is composed of different particles, and then these particles can break. Then it is bendable, or so. But in our it's rigid, like block, so we are not able to bend this block. But the thing is, we are more focused on the ballast part, especially how the force is transformed from the top to bottom. So we don't think like the rigidity of the cross ties will affect that force chain anyway. So
don't you think in the expansion and the load distribution?
yes. So the the distribution we think is going to be different, especially for the full support condition case, because in other conditions, it's non-deformable. But still, I mean, you have a gap between it, so it's not going to have any force anyway. So it's not like, as you can see in the calibration part, the other part doesn't change a lot, doesn't support conditions, but only this full support condition may have some problems with how the force distribute. Yeah, you are right.
My other question is related to the aggregate material itself.
Mhm.
So you mentioned more, you were talking about the big picture, but I was wondering for the aggregate materials, I saw that they have different shapes. So do you use the same material property, and what material behavior do you use for aggregate?
By behavior, you mean the modulus?
I mean, yeah, do you use linear elastic?
We use linear. We use K theta model actually. Oh no, we use linear elastic models. Yes.
And the material property, like of the modulus, is it the same for all of the aggregates?
It's the same for all the aggregates.
But at this point, when you have this technique, I think, can you use the one that you get as version material?
That's a good question. Is that because we have to create the particles first. In that phase, we'll give them like properties to create them. And for example, if I understand it correctly, so for example, for aggregate materials, it's stress hardening or something. So they can have a little different properties if you change the loadings, right? But actually, if we already create these particles in this model, we have to give it a property. And this time, we don't have the loadings yet. That's why it's a little difficult to have it nonlinear or.
You know what I mean? There might be some differences.
Oh.
Not all of the aggregates are the same. Do you use
I see.
material properties for all of them?
We actually can create different material. For example, we can create a bunch of aggregates with this type of material and this with another. But in this case, we don't. We didn't. We just create one type of material to make it simple. Yeah.
You were talking about multiple scenarios.
Mhm.
I totally agree because every time that you see a problem, it's one of these scenarios.
Mhm.
But how do the spacing, like, a lot of conflict between the main and the ballast. If it's small or large, how did you select the one?
We actually selected with the common gaps we found in the field. But as you see, that in the field it can have multiple scenarios. You may have large gaps or small ones, but we only simulate one type, which is around 3 millimeters. Yes. Yeah.
I have one question. And, when you were tested for the study, the load was varying between 10 and 25 kilonewtons?
Yes.
But for the dynamic case, it was almost 80 kilonewtons.
Yes, because in these are like two different, how to say, these are like two different phases of the study. First phase, we study the static loading. So in that case, we study the lab testing loading levels, which is the 10 kips, and then the field loading levels is 20 kips. And then we have, if there is an increase in the loading levels in the future, it may be 25 kips. So we choose 3 types. And the second one you mentioned, that is not real seat loading. That is the wheel loadings. So that's maybe the difference. Because when we show it, it's not the real seat loading. We show like the, so here, we show that this is the applied loadings on the ties, which is like 2 times of the loadings of the real seat and everything. So it's not a real seat loading. It's not comparable to the other one. Yeah.
Thank you for your presentation.
Mm-hmm.
I have 2 questions. So the first one is how to build the angular particles in block 3D. Because I used PFC before, and they only provide balls. Like, so
Yeah.
if you want to build the angular particles, you need to clump them all together. So my question is, how do you use like the angularity, the flap, those properties to build the angular particles?
That is the major difference between like block 3D and PFC actually, because PFC they use like balls to simulate all the particles, and you clump them together to make different shapes. But in the block 3D, it's just for angular particles, because in their libraries there is no ball. You can create a ball in the library, but the mechanics of how it works is not based on the balls. So you can create different shapes in your library directly by giving like angularities, flat elongated ratios, and giving their like how many faces you want, and what is the centroid of this particle. So block 3D is one that you can create angular particles directly instead of clumping.
Particles to generate a random particles.
Yes, we select like the probability, not probability, like the percentage of particles. For example, we have a bunch of libraries. For example, we have 30 libraries for different types of materials. Each one have different angularities and elongated ratios. Then we can say like we select 100 pieces from this library and select 200 pieces from this library. So we give them a percentage of how many particles we select from each library.
My second question is, how do you design the mechanical properties of each particle? Like you mentioned the stiffness of each particle. But when we talk about stiffness, we usually like run some tests to get the stiffness of some material. But here you want the stiffness of each particle. So how do you do that?
We actually choose these like parameters in the DEM. We choose the gradations and particle shapes based on our field. But like you said, the stiffness, we choose it from the literature. So some of the literature, they already validate their like properties in their laboratory testing with their DEM, and we choose the same parameters with those as a normal contact force.
So my third question is, the model, like the glass model you do here, is it the same size as the real field?
You mean the whole model?
Yeah.
Yes, it's the real size.
So the particles you do here, are they the same size as the real?
Yes, the grain size of the ballast particles are the same with the gradations are the same with the field. Yes.
So, okay then.
Thanks.
Any more questions? So let's take 4%.